Welcome all to the lecture on vector fields. See, here you consider this example. Phi of xyz is equal to x plus 2y minus 3z. You can see that it is a function of three variables. And moreover, if we take a triple xyz, its image via the function phi is x plus 2y minus 3z. Here x, y and z are real numbers. So their sum, scalar multiples, difference and so on ultimately gives a real number. In other words, here we get phi of xyz is equal to x plus 2y minus 3z gives a scalar corresponding to each triple xyz in the domain of the function phi. Such functions have a special name hereinafter, and that name is scalar field. Now let us see the exact definition. A scalar field is a scalar valued function of three variables. That is, any function of the form phi of xyz can be called a scalar field. Yes? And there are so many applications for this scalar field in natural life. We see, for example, the water pressure at each point in the ocean is an example of a scalar field, because pressure is a quantity which have only magnitude, no direction is there. Similarly, the temperature at each point in an insulated wall is also an example of a scalar field. These are applications that you can see in the physics class. But for a mathematics student, everything appears in the form of a function. So we can say that phi of xyz is equal to x square plus y square plus z square is also an example of a scalar field. Now, if phi is a scalar field, any surface given by phi of xyz is equal to c, where c is a constant, is called an isotonic surface or a level surface. See, here phi is a function of three variables, and we put that is equal to c, so that what happens, phi of xyz is equal to c is the set of all triples x, y, z for which phi of xyz is equal to c. So such collection of triples form a subset of the space, three-dimensional space. So such a subspace will be a surface, and that surface is called a level surface. Okay, let us consider an example. Suppose our phi of xyz is equal to x square plus y square plus z square. Okay, and suppose we put this is equal to 3. This is equal to 3. Then what happens? When we put this is equal to some constant, then this becomes a surface. That is the definition. And such surface is called a level surface. Here, if we put phi of xyz is equal to x square plus y square plus z square is equal to 3, equal to 3, 3 is the constant, then it becomes a sphere in three-dimensional space centered at the origin and having radius square root of 3. Yes? Now we consider one more example. Phi of xyz is equal to x square plus y square plus z square. Same scalar field, but we equate that scalar field is equal to 10. So this also again gives a sphere centered at the origin and having radius square root of 10. Okay. Now let's consider some more examples. See, now what about phi of xyz is equal to x square plus y square plus z square? Simply, if we simply write, that represents a family of spheres with a center at the origin. Why? Because we have seen that if we put it is equal to 3, we get a sphere like this. If we put c is equal to 10, we get a sphere like this. So in general, This phi, this scalar field represents a family of spheres with a center at the origin. Similarly, the scalar field x plus 2y minus 3z. See, if we put this is equal to C, then it represents a plane, because you all know that the general equation of a plane is ax plus by plus cz is equal to d, and such a plane will have a normal of the form ai plus bj plus ck. So that by looking here, our capital A is 1, 2, C is equal to negative 3. And so here this phi represents a family of planes perpendicular to the vector I plus 2j minus 3k. P of xyz is equal to square root of x square plus y square minus z represents a family of cones. In physics also, the level surfaces have a special or a name, and such surfaces are called equipotential surfaces. If phi denotes the temperature, they are called isothermal surfaces. Equipotential surfaces occurs in the case of gravitational field or electric potential and so on. Vector fields is also a function of function. Vector fields also a function, but the difference between scalar fields and vector fields is such that vector fields produces vectors. Already in the discussion of vector valued functions of one variable, vector valued functions of a real variable, we have there are functions of the form r of t, which is equal to x of ti plus y of tj plus z of tk, which produces a vector corresponding to the parameter t. And if the final term, if it is of the form r of t is equal to x of ti plus y of tj alone, it becomes a function, vector valued function that produces a vector in the xy plane. That are already familiar to you. Now here the difference is that here also we obtain a vector m of xyi plus n of xyj. But the difference here is that here our function has a domain which consists of elements of the form ordered by xy, ordered by xy. So ordered by xy's are points on some subsets of the xy plane, isn't it? So this f of xy, which produces the vector m of xyi plus n of xyj, is a function from the subset of the xy plane, and it produces a vector. So these type of functions are called vector fields, and these vector fields are defined on subsets of the xy plane. Similarly, if we have a function of the form f of xyz is equal to m of xyzi plus n of xyzj plus xyzk, this is also a function, and here f has a domain which consists of triples xyz, and such triples are from a subset of the xyz space. So this this function is called a vector field defined over a subset of the xyz space. Now we give a precise definition of the vector field. A vector field is a vector valued function of three variables. That is, a vector field f is a rule associating with each point triple xyz of a region in space, and corresponding to each triple xyz in the domain, we get a unique vector f of xyz. and it has the form as mentioned above. Okay. The vector field is continuous if the component functions m, n and p are continuous. What are the component functions? M, n and p. Don't think that m, n and p are constants. They are again functions. See here m of triple xyz is a function and this is a scalar valued function. M of triple xyz produces a scalar and that scalar I gives a vector. Similarly, n of triple xyz is a scalar, p of triple xyz is another scalar, and we used such scalars to get the vector f of xyz. Also, if m, n and p are differentiable functions, differentiable scalar valued functions, then f is also differentiable function. As mentioned earlier, if there are only two components xy ordered over xy, then we get a vector field involving I and j alone. Some examples of vector fields are f of xyz is equal to xy square I plus 3yz cube j plus 2x square z. You compare this with the definition. You can see that in place of m of triple xyz, here we have xy square. Here we have xy square. What's that? That means xy square is a scalar valued function. Similarly, n of triple xyz, 3yz cube is again a scalar valued function. 2x square z is a scalar valued function and so on. Similarly, there is one more example. xi plus yj by x square plus y square. While defining this function, you note that even though our domain is a point from triple x, y, z, it produces a vector xi plus yj by x square plus y square. And here we have to take a caution that here k component is absent, so that this produces a vector in the xy plane. And also we have to note that this function is well defined only when x square plus y square is different from 0. What are the points? When x square plus y square is equal to 0, x square plus y square is equal to 0 only when x square is equal to 0 and y square is equal to 0. That is when x is equal to 0 and y is equal to 0. So such a situation happens only when ordered pair xy is equal to ordered pair 0, 0. So that this function is not defined when x is equal to 0 and y is equal to 0. What is the situation? If we take a point triples xyz where xy is 0, both happens. When one situation is the origin. Is there any other point? No, no other point. This is some example that is applicable. You can see in the physics textbook, you can see such examples. See, you can see that the airflow around an airplane can be described by means of a velocity field, because a vector can be assigned at each point representing the velocity of the wind at that point. Okay, this is the situation. Some airflow goes under and some airflow goes over. And this is an artery, okay, and it shows the laminar flow of the blood, and the blood flows fastly in the middle. Okay, such situations can be described in terms of vector velocity field. Velocity field means this is an example of a vector field. The laminar flow of blood in an artery. Artery is a cylindrical layers of, and you can see that blood flow faster near the center of the artery. This can be represented by means of a velocity field. Another example is inverse square force field. In physics class, you have studied such fields. This is also an example of a vector field. This is again lines of force. If we have two charges of the same sign, positive charges, then this shows the lines of force around two equal positive charges. These are examples of vector fields. Now we are going to draw the graph of a two-dimensional vector field. F of xy is equal to negative yi plus xj. How to draw the graph? Drawing the graph is not an easy job. Okay, what we do here is this: we choose some points in the xy plane and then graph the vector f at the point. Okay, before giving the details, I give you how it appears. See, here we need a field like this. Here you can see that there is a point ordered where 1 1. There you can see a vector here. Okay, so here we are going to do like that. So one method is to choose points in the xy plane and then graph the vector f at the point. For example, consider the point ordered where 1 1. Then what will be f of 1 1? F of 1 1 means x is equal to 1, y is equal to 1. So this becomes negative 1i plus 1j. So it becomes negative I plus j. That means at ordered where 1 1, okay, this velocity vector field, this vector field produces a vector negative I plus j. So what we do is we take the point ordered where 1 1. There you plot the vector negative I plus j. Okay, here corresponding to here we have a circle having radius 1 and we consider ordered where 1 0 here, and here there we have already noted that f of 1 0 is the vector j. J vector means we draw a vector parallel to the positive direction of y axis and this vector have magnitude 1. Similarly, ordered where 0 1, f of 0 1 is negative y, so we draw a vector parallel to the negative direction of x-axis and having direct magnitude negative, magnitude 1, direction is opposite to the negative direction. We go to the negative direction. Similarly, negative j is a vector parallel to the y-axis and in the direction of the negative x-axis going down, and this also have the magnitude 1. Similarly, the other one. Okay. Now what we consider is k is equal to root 2. We put k equal to root 2. K equal to root 2 means we get x square plus y square is equal to 2, and this is a circle having radius root 2. Okay, and we list some points on this circle. You can see that ordered where 1 1 is a point on this circle because 1 square plus 1 square is 2. Similarly, other 3 points are ordered where negative 1 1, negative 1, negative 1, 1, negative 1. Okay, and putting these values, you can see that from this f of xyz is equal to negative yi plus xj, you can see that the corresponding vectors are negative I plus j, negative I minus negative j, I minus j, I plus j. Okay, so it gives root, same length root. Now we put a k equal to 2. Then we get the circle x square plus y square is equal to 4, and we have the 4 points. Ordered where 2 0 is a point here because 2 square plus 0 square is equal to 4. Similarly, other 3 points. So putting x is equal to 2 and y is equal to 0, this f of xy is equal to negative yi plus xj gives 2j, the vector 2j. Similarly, we obtain the other 3 vectors. Okay. Now we are going to plot those points. This is the circle of radius 2 and ordered where 2 0 is a point there, and 2j is a vector from ordered where 2 0, and it is parallel to the y-axis. Direction is upward because there is a positive symbol here. Magnitude is 2. Similarly, the other three vectors can be drawn. And on the circle having radius square root of 2, we have the point ordered where 1 1 here. And corresponding to ordered pair 1 1, we have observed that negative y plus j is a vector. What is negative y? How to get negative y? Negative y is obtained by putting one unit in the negative direction and parallel to the x-axis, one unit in the positive direction of the y-axis, and reach at the point. Then join these 2 points. See, you can see a triangle law of addition is applicable there. So we get, similarly the other 3 points can be obtained. Now we define a new term. The gradient field of a differentiable scalar function f of triple xyz is the field of gradient vectors, and this is called gradient of f, or shortly grad f, and grad f is equal to del f by del xi plus del f by del yj plus del f by del zk. This is a definition. See, f of xyz is a scalar valued function, and we take the derivative, partial derivative of f with respect to x, and we get a scalar. Partial derivative of f with respect to y, we get a scalar. Partial derivative of f with respect to z, we get a scalar. And using those 3 scalars, we get this vector, and that vector is called the gradient vector or gradient field. Corresponding to each triple xyz in the domain of f, there will be a vector given by grad f. At each point, there will be a vector. So this grad f is called a vector field, and this is the gradient vector field. It connects the scalar field f of xyz with a vector field. Okay. And why we stress the point that this is a differentiable scalar function. F of xyz is a differentiable scalar function. Why? Because here we have to have the partial derivatives. That is the reason. Now we consider some example. F of xyz is equal to, so we use the definition. From the definition, immediately we obtain this one, because our f of xyz is xyz. So what is del f by del x? Del f by del x is partial derivative of xyz. While evaluating the partial derivatives with respect to x, we treat other variables as constant. So that will be yz. So we get yz here. Similarly, the partial derivative of f with respect to y is keeping other variables as constant. We get xz. This is xzj. Partial derivative of f with respect to z is xyk. So we get the field yzi plus xzj plus xyk. Next, we have to find the unit normal to the surface x square y plus 2xz plus 2xz is equal to 4 at the point triple 2, negative 2, 3. See, here we are asked to find the unit normal to the surface x square y plus 2xz is equal to 4 at the point triple 2, negative 2, 3. Now the surface is it is a level surface corresponding to the function phi of xyz is equal to x square y plus 2xz minus 4, corresponding to the value c is equal to 0. C is equal to 0. So grad f is normal to the given surface. Grad f is normal to the given surface. And what is grad f? Grad f is, we first find the partial derivative with respect to x, I, partial derivative of with respect to y, then j, partial derivative with respect to z, k. So if we find the partial derivative with respect to x, we obtain. So you get 2xy plus 2z I plus x square j plus 2xk. Now putting x is equal to 2, y equal to negative 2, z is equal to 3. This simplifies to negative 2i plus 4j plus 4k. Okay, this is a vector. Okay, at the point triple 2, negative 2, 3, and at that point that vector is normal to the surface given by this one. So a unit normal will be obtained by dividing this vector by its magnitude, and so we get this answer. Now this is not only the unique unit normal vector, another unit normal vector also can be obtained by multiplying this one with the negative 1, and that is 1 by 3 I minus 2 by 3 j minus 2 by 3 k. Suppose we are given with the vector field r is equal to, this is not a simply a vector, this is actually a vector field. Why this is called a vector field? Because even though I simply write this as r is equal to xi plus yj plus zk, this is actually r of triple xyz, and that is equal to xi plus yj plus zk, that is a vector valued function. And we are asked, and it is given that absolute value of the vector valued function is given by r. Then we have to show that gradient of 1 upon r, here r is a scalar valued function, that is equal to negative r by r cube. See, even though here we simply write like this is actually, even though we simply write r, that means it is a function of 3 variables, and absolute value of r at xyz is the absolute value of the vector r of xyz. What is vector r of xyz? Vector r of xyz is the vector at the point triple xyz. See, gradient of 1 upon r is, by definition, what is gradient? Gradient is partial derivative with respect to x, I, partial derivative with respect to y, j, partial derivative with respect to z, k. So we do like that. Now what is partial derivative of x of 1 upon r? 1 upon r is a function. Though we have simply write r, it is a function of 3 variables. So don't think that 1 upon r is a constant. Okay, it is a function. So here del by del x of 1 upon r, that is partial derivative of 1 by r with respect to x, cannot be directly found out. We apply chain rule there. Okay, chain rule, you have seen chain rule while discussing function of 2 variables or function of 3 variables and so on. So you have to refer such topics. So if we apply the chain rule, what we get? Del by del x of 1 by r is del by del r of 1 by r times del r by del x. Okay. Now what about del by del r of 1 by r? Del by del r of 1 by r appears in the form of d by dx of 1 by x. What is d by dx of 1 by x? D by dx of 1 by x is d by dx of x to the power negative 1, that is equal to negative 1 times x to the power negative 2. Similarly, so it simplifies to negative 1 upon x square. So here in place of x we have del by del r of 1 by r. So we get negative 1 by r square. Okay. Similarly, here we have del by del y of 1 by r is del by del r of 1 by r times del r by del y. Similarly, the other one. So now what about del r by del x? So here you can see that negative 1 by r square is a common factor and we take it outside. See, this is a scalar corresponding to a fixed triple xyz, but actually it is a function for a. So this is I. Now what about del r by del x I plus del r by del yj plus del r by del z k? Okay, that means r of xyz, the scalar function r of triple xyz is obtained by taking the absolute value of the vector field r of, not the vector field, the vector r of xyz. See, if we fix a point at triple xyz, there we will have a vector r of xyz and we take the magnitude of that vector, and that magnitude is a scalar, and that scalar is r of xyz, isn't it? Now what about the vector r of xyz? Vector r of xyz is xi plus yj plus zk. So its magnitude will be square root of x square plus y square plus z square, isn't it? That is, r is equal to square root of x square plus y square plus z square. What about then r square? R square will be then x square plus y square plus z square. So here we use that idea. R square is equal to x square plus y square plus z square. Okay. So what happens? We differentiate it throughout. Then what we get? 2r times del r by del x is equal to 2x. The remaining 2 will be y square and z square. The derivative with respect to x will be 0. So what we get is 2r times del r by del x is equal to 2x. So 2 will be get cancelled. So we get r del r by del x, and from that we get del r by del x is equal to x by r. Similarly, we can see that del r by del y is equal to y by r, del r by del z is equal to z by r, and so on. And we put those values here. Yes. Now here you can see that r is a factor here, and we can take it outside. So this becomes negative 1 by r cube xi plus yj plus zk. What about xi plus yj plus zk? Initially we have taken it as r of xyz. So we put here. So this becomes negative r by r cube. Now we consider, we have one more example. We have to find del of f of r is equal to 1 by r f prime of r. What about del of f of r? F of r is, f is a function, any function, we don't know what that function, but it is a function of the variable r. What is the variable r? R is the variable scalar function here, r of xyz. Okay, and it depends on 3 variables x, y and z. You remember that. Don't think that f is a function involving r. R is not an independent variable. It is a dependent variable. It depends on x, y and z. So ultimately this f depends on x, y and z. And this f of r is a scalar valued function, and we find the gradient of that scalar valued function, and that vector field is equal to 1 by r times f prime of r. 1 by r is a scalar. F prime of r is again a scalar because it is the derivative of the vector. F prime of r is a scalar valued function. It is the derivative of the scalar valued function f of r. So this is a scalar times the vector r. So ultimately this is a vector. This is actually a vector field because corresponding to each ordered by xy set we have a vector. So this becomes a vector field. By definition, what is grad of a function, grad of a scalar valued function? It is partial derivative with respect to x of that function I plus partial derivative of that function with respect to y j, partial derivative of that function with respect to k, isn't it? Now what about partial derivative of f of r with respect to x? Already I have mentioned that don't think that f is a function depends on the only the variable r. It is the r is also a variable, depends on 3 other variables x, y and z. So partial derivative of f with respect to partial derivative of f of r with respect to x means again we have to use the chain rule. Okay, that means del by del r of f of r, del by del r of f of r times del r by del x. What is del by del r of f of r? Del by del r of f of r. You compare del by del r of f of r with our ordinary derivative d by dx of f of x. D by dx of f of x. What is d by dx of f of x? D by dx of f of x is f prime of x, isn't it? So similarly here d by dr of f of r can be is actually f prime of r. So f prime of r del r by del x. Similarly the other one, other two one. So again we continue this process. We bring common factors outside. What we get? What is del r by del x? Del r by del x we have already evaluated that. Del r by del x is x by r. Substitute that one. Then again bring the common factor r outside. So you get like this. What about xi plus yj plus zk? This is vector r. So we ultimately end up with the f prime of r by vector r by r.